Hi. That question is about calculus itself, but it's useful for the part of waves and fluids because, for example, that equation, it has an application in the Euler's equation for the fluid, and so the background of that question, there is physical background, of course, but at this level, the question here we have is just to prove an identity, and that identity is written there as u dot with gradient of u is equal to the curl of u cross u plus the gradient of u squared over 2. I just wrote the start of the solution number 2, which would be starting from the left hand side and proving the right hand side. But that's not important. I prefer the solution is better done if you start from the right hand side and rewrite the right hand side, and then you prove that it's equal to the left hand side. And that's what I'm going to do here, because then we can train the index notation or Einstein summation rule. And that's the purpose of that question, of training that, understanding that. But again, that equation, it has relation to the Euler's equation for the fluids. And just before the first step, I just have a comment here, which is the following. Sometimes you can be confused about what's the u vector square, right? And that needs to be understood as a scalar product of u with u. And therefore, that's a scalar quantity, not vector. And of course, it has to be scalar because we are taking the gradient, and the gradient of something, so that thing inside the gradient has to be a scalar function, not a vector. And so this u square is a scalar. And in particular, this is equal to the modulus of the vector u square. Just an observation is sometimes you need to be careful with the notation, because sometimes people write the modulus of a vector, let's say vector u, to be u, and then you can confuse u with the modulus of u, and then and that's a in that case here you could write u square, or you could also write the modulus of u square, so that's just like u square. So as you can see, the notation can be a bit misleading, but just remember that what we are dealing with inside a gradient is a scalar. Therefore, the only way which we can create a scalar out of vector with itself is the vector scalar product with itself. It gives the scalar. Yeah, so just this information about the understanding of u square, and then the first step. So now, what's the first step? So the first step is I'm going to open this term here, expand these terms with index notation, so that epsilons of I, j, k's, so forth and so on. But the first part is, so I have this term there, right? And I'm choosing, you need to choose, you need to prove it. So what we need to start with is to choose an index where you write everything in terms of. So here we are choosing the index I, right? So that means that everything there will be written with free index I. All the other index are not free index, they are dummy index. So they are all summed. And need to be careful that for each term individually, when we have each term as a single piece, we cannot have more than twice the same index. So we cannot have the same index 3 times. But we will see that when we have a sum, in that case we have 2 terms there, the gradient plus the curl, the cross product with the cross product. We can repeat the index for the other term, because this second term is independent. This second term is independent of that one. But that's we can see it later on. So now we just write the I component of this cross product here. So it's epsilon ijk. So epsilon of ijk, and then the second component goes to the j, and the second component goes with this guy here, and a goes with that guy here. So this guy is j, this guy is the k. So j is summed with j and k is summed with k. So that's the first part. But now we need to open this guy here. So we need to write the component, j component of that guy here. So, and again, we have another vector product. So we will gain another epsilon, right? So this other epsilon here. So now we need to open the j component. So it's not any component, it's the j component, because here we wrote the j component. And now we expand this in terms of the j component. So the j component starts with epsilon j, and then I choose two different letters because I already used I and I already used j and k. So then I choose here L and M. So here L and here M. Now I have this extra bit here, so I just need to put it back here, right? So if we do that, now you have we have two epsilons here, right? And this term, we just repeat this term as before. And then this line here is basically using the identity that epsilon is completely unsymmetrical object, right? When we have a cyclic change of the index, it keeps unchanged. So it's +1. It will not affect. But if we change any of the index in an odd way, so not cyclic, then we get the -1. And as you remember, these epsilons are completely unsymmetrical, so if one of the index are equal, then everything is equal to 0. But basically, as you can see here, what I did from here to there, I just changed the order of this term with that term, and I kept all the rest unchanged, right? So what I did here was basically just I just used that I of I j k is equal to I of, so it's a cyclic change, so that's a j k I. As you can see, that's cyclic. So I j k I j k I j k, and particularly I chose the jki. You can see here jki. Now, why I did this is because, of course, I want to use the identity of the product of the epsilon of the epsilons as delta delta. So now I just apply it here. So this product is given by that combination here with k with L, I with M, and then the inverted one. So I with L and M with K is here, and there is a minus here, just the identity here, and repeat everything else. And then you know how the delta works. The chronic delta just change the index whenever you choose that index to change for the other index. And we want to keep I always there, because I is what we decide to expand everything in terms of, right? So we always keep I. The other ones, they are not important. You can choose, for example, here we have a KOL. Which one you should keep, KOL? It's up to you. You can decide, but you should not decide about the I, because you decide to open here with I. So keep, whenever you see a M, change M to I, because at the end of the day here, we want to keep this I, all right? So then if you do that, just simplify here, multiply, change L to K and change M to I, just here, you do that. So that first term here changed to K, U, I, U, K, and the other one is L, we change to I, M, we change to K, and K, we keep K. So that's it. So that's the first part here, which corresponds to this bit here, guys. This part here. Now we need to open that part here, right? The gradient of the U square. Now I want to highlight stress that's important here. This point is important because which variable, which index should we choose here? So if the question, so I think that's an important thing of the question is, so if the question was just to open that, we could choose any index on your choice, and that's fine. But here we are summing. So we are summing this term with that term. So if we already have decided to open this term in terms of I, therefore we have to open this one in terms of I, because you want to sum the I term is like the x vector with the x component, the y component with I component, so far and so on. We don't want to mix. So here we are forced to choose the I component. That's mandatory here. And then, so that can be written as I, but u square, we can write it as, you can choose any letter because this is a sum, so that's a dummy index. So I can really change here uj, no problem. Doesn't matter that I used it before, because that other term, it's independent of that one here, so no problem. And here, because we have these two guys that they are the same, that's basically the two cancel out, and then we multiply this Leibniz rule, the derivative of the product, so is the product of the derivatives, and then there's the sum ij. Yes, because yes, we have 2 times this, and then we have divide by 2, so that 2 goes out. So now what we do, we just put everything together. So we already have the first term, we have the second term, and we just place all together. So all together, we have this first term here plus what we just calculated here over there. And then we have 3 terms. Now what we do, well, this point here is important as well, because to mention, which is, so a priori you could think that is not equal, right? Because here we have I, and here we have I, all right, but here we have J, and here there we have K. But they are the same actually, so they cancel out, because again, this is summed, right? And this is summed, so they are dummy index. So you can change it whatever you want. These pieces, they are independent pieces, right? So here where there is JJ, it actually is, I can say that's UMM, or UC. But of course, I can also see that's K, so they cancel as well, because that's basically the same. It's the same, so they cancel out. And then what's left here is just the first term here, right? Just this first term here, and then we just need to interpret it. So here we have a summation, because we have K with K, right? And we have this index I alone here. This is a free index, that's right, because we decided to open everything in terms of I, right? You remember we open here everything in terms of I. So this term is a free index, this is summed, that's fine. So that's what's K with K, that's a scalar product. So that means we have a scalar product of U with the gradient. Here we have U with the gradient, scalar product. But this is a scalar thing, right? Because that's there's a scalar product, so therefore that's a scalar thing. But we still have left here the bit, which is the UI, but U is a vector. So basically we are saying that that's that quantity. If we check the U scalar with the gradient, apply this to U, which is a vector, and then we check the I component, and that's exactly what we have here. So the K comes out with this differential operator, and what's remain is this I here, which is here. And this equation, this identity is very useful for the Euler's equation in the fluid, and that's it.